All right, welcome everybody, bright and early in the morning to Zach's defense. As is the tradition at IFA, I get to talk a little bit about Zach before we put him up in front of you and he gets to tell you what he's done. He's going to tell you all about the cool science stuff he's done, and I get to tell you about all the other stuff that has happened in the meantime. I promise most of it's nice. So Dan had a really great idea yesterday. So we keep everything. And I got this email, and I checked the date on this. I was actually still negotiating my start date here. I didn't even know when I was showing up. I was going back and forth about coming sometime in September. I got this email. And at this time, I had never advised a student before. I don't know, like Zach is not only my first grad student, but my first student period ever, any sort, right? So I get this email. I say, sure, why not, right? And I visited for the IFA 50th, and Zach like, let's meet in person. I pitched him a project. He's like, okay, let's do it. And that was where this started. And since then, I have been working with Zach, both for his 699 and obviously his PhD. So Zach has saved my bacon many times with coding. He had the misfortune of being my student at the same time I was learning Python. And it turns out he's very good at Python, and I am really not. And so there's lots of, like, this is Zach in front of a room full of high school students at High Star teaching high school students Python. They were probably better listeners than me. And he's written all these repositories. He gets emails from me that look like this. On a fairly regular basis, and you know, Zach will tell you I'm not the most responsive by email sometimes, and so most of these were at the end of a meeting. I'd be like, "Hey, can you tell me why this is broken?" And he always helps. So you can see that the end of his PhD is straining him a little bit. This was sent to me by Pete. And for a split second, I was like, wow, maybe he isn't. But more seriously, Zach has done, while I've been here, has done a ridiculous number of things in terms of like service record to IFA and time put into trying to make this place a better place. Zach competes with the best of us. He's been on all these committees, right? These are pretty much committees I've also been on, right? He's served on all of them. And I don't have any good pictures of this because it's all, you know, we're all very serious when we're sitting on committees. But things like the director search, he's done grad admissions, he's helped to get this grad mentorship program off the ground so that there's more of a support structure. Was grad rep for a while, and over the course of the many years working with Zach, I've had wonderful conversations with him about basically the craft of what this is, not just the science, but also the social aspects of how we go about doing science and how we do it in a way where everybody is treated well, right? So I really have appreciated that time with Zach. He's been, as you could have guessed, right, hugely involved in outreach, right, from online things during COVID to High Star programs to Astro Day, all of these different events. He's as involved in those as he was in internal IFA workings. And this is, you know, a small fraction of the pictures that I extracted from the people that helped me out. Of course, it hasn't been all work and service and all those things. Lots of fun in Hawaii. I tried to say there were some good ones in there, but I don't know the context. So it's been a wonderful time having you here. Thank you for being such a wonderful first student. And I think it's time to take it away. All right, just as a reminder, what we're going to do is Zach is going to give this talk. We're going to do questions for the audience afterwards. Committee members, please hold your questions until the closed session. Then we'll ask everybody who's not on the committee to leave. We'll grill Zach for a little while, and then we'll be done. Okay, now you take it.
Awesome. Jen, thank you for that introduction. It's been a really awesome experience working with you. We'll say more about that later. But I am super excited to get to share with you guys what I've been working on for the last 3+ years. Been a lot of work and a lot of really cool results. So let's dive in to rotational characterization of stars in TESS using deep learning. Let me make sure this works. Cool. So let's start with the question. Why rotation? All stars rotate. If you look up in the sky and you see a star, it's rotating. Whether we can detect it or not, it's spinning. And that spin, that rotation has some effect on the nature and the character of that star. Rotation is related to things like magnetism. With convection, rotation powers magnetism. Rotation tells us things about the transport of angular momentum in stars. It's connected to the spots, the dark spots that are on the surface of stars. We detect rotation because dark spots on the surface of stars rotate into and out of view, affecting the brightness of those stars as a function of time. So rotation tells us about spots, and spots tell us about rotation. Rotation also can be used as a lever to get characterization like ages for stars, and because we can characterize stars with rotation, we can understand the planets that orbit them. And of course, rotation tells us about the sun, and the sun is our anchor for understanding how rotation behaves in stars as a function of time. Just to give a little bit of an example here, stars spin down as they age, and this was first noticed by Andy Szymanich in 1972. The important line here is the one that is marked "rot." Szymanich noticed that the rotation velocity of stars decreases as a function of age. Now, ages are very difficult to get for stars. Normally, we have to rely on things like isochrones, which require stars to change in their brightness as a function of time, but stars that are cooler than the sun don't really change that much in brightness. So we need other means to get their ages. Ages are very difficult, but because stars spin down as they age, the fact that we can measure rotation means that we can use rotation to estimate the age of those stars. And so rotation becomes a very nice anchor for the characterization of stars. We can also see this in the open clusters. Open star clusters are these really nice samples of stars that are born at the same time. They have the same composition, and they have a range of masses. And so we get really interesting information of how rotation behaves as a function of time with these snapshots of stellar evolution. We can start at 120 million years old with the Pleiades. You can see that the warmer stars fall along this nice tight sequence, but then there is some spread in stars cooler than about 4,500 Kelvin. If you fast forward a little bit, you go to 670 million years with Praesepe, you can see that the more stars are on this tight sequence, and there's still a little bit of a spread in the coolest stars. And generally, all of the stars in Praesepe are spinning at slower rotation periods than all of the stars in the Pleiades. So we can see, as we fast forward through time, this change of rotation with age. Let's show some more. Things start to get interesting at about 1 billion years old. The open cluster NGC 6811, while the hottest stars have continued to spin down with time, in the cooler stars, the sequence actually lies right upon the sequence of Praesepe. These two sequences are two different ages, but there's some interesting stalling in the spin down that causes the rotation period sequences to lie on top of one another. By 2.7 billion years, we see the cluster rubric 147, where spin down has resumed. There's been quite a lot of spin down in the hotter stars and a little bit in the cool stars, but there's this really weird dip that we didn't see in the younger clusters. And so something interesting is happening with this rotational magnetic braking. And we can also see it a little bit in M67. But this is just a nice illustration of how we can use open clusters to take snapshots of rotation as a function of age, which we use to calibrate a process known as gyrochronology, where we use rotation to get a chronology or ages of stars. This makes rotation a very powerful tool. We can use it to characterize stars and the planets that are around them. As I mentioned, most age determination methods rely on some form of isochrone, which is driven by the brightness of stars. But stars that are cooler than the sun don't appreciably change in brightness as they age. Instead, we have to use their rotation to understand how they, because they spin down with time, we use rotation to get their ages. So for the coolest stars, which also are the most abundant stars in the galaxy and also host many, many, many exoplanets, as we have found with missions like Kepler and TESS, we have to use rotation to be able to precisely characterize these stars. We also get a nice picture of stellar rotation with a field star population like what was seen in Kepler. Kepler gave rotation periods of over 50,000 cool main sequence stars. This is taken from Angela Santos's work over the last 3 or so years. We look at this with rotation period on the y-axis, temperature on the x-axis, and a field star population is a mix of masses, ages, and compositions. And so rather than these nice tight sequences, we see a spread in rotation across temperature and age. As a field star population evolves and it experiences different mechanisms of spin down, it carves out features in this period distribution that tell us how the stars are evolving. For example, the lower edge on this is a slowly rotating sequence by which the field stars have converged onto. Stars are born spinning rapidly, and across time, they slowly converge onto a nice rotating, slowly rotating sequence where gyrochronology becomes valid. The upper edge of this distribution is carved by, in the cool end, you see the oldest stars in the galaxy that have had time to spin down to these long rotation periods. In the hotter end, hotter than about 5,500 Kelvin, so over here and hotter, stars undergo what is known as weakened magnetic braking. At some point in their lifetimes, they stop spinning down. And so they don't reach the long periods that we see in the cool stars. Instead, they have this pileup that's seen just along the upper edge of the hot star distribution. There's also this really weird gap. What makes a gap like that? There are people with some pretty strong opinions on what makes this gap. One idea is that there is some fundamental change in the nature of rotational braking, where there are actually no stars here. They might stop spinning down and pile up on the bottom edge of the gap, and then start spinning down at some point later, where they move across the gap and leave behind a true deficit of stars. Others have suggested that maybe there is some interplay between bright faculae and dark spots on the surface of stars where they might cancel each other out, making rotation very difficult to detect on their surfaces. Whatever causes these features, understanding how this distribution is sculpted is going to tell us how stars evolve in their rotation and their structure across time. Now, Kepler gave us some really awesome insights into the picture of rotational evolution, but Kepler was ultimately limited because it was one mission staring at one field in the sky, giving us access to a limited number of stars. If we want to understand how rotation behaves across the entire galaxy, if we want to understand the fundamental nature of stars as they spin down over time, we need 1, more stars to sharpen the features of this distribution, and 2, we need them in more parts of the sky to make sure that what we see in Kepler is the same as what's seen elsewhere in the galaxy. And this is where TESS comes in. Now, TESS is the Transiting Exoplanet Survey Satellite. It's primarily an exoplanet finding mission. Ashley gave us a great introduction to TESS yesterday in her successful thesis defense. Congrats, Ashley. But in its search for exoplanets transiting other stars, it collects light curves, time series brightness measurements for stars all across the entire sky. And these light curves we can use to look for rotation. So TESS technically even studies stars. TESS is all sky. You can keep laughing, that's fine. TESS is all sky, but the real power of detecting rotation comes in 2 continuous viewing zones located at the ecliptic poles, one in the south, one in the north. These regions of sky are 450 square degrees in area. They're larger than the Kepler field, and so and they're observed for about a year at a time, continuously. So we have the potential to get more stars rotating in the TESS continuous viewing zones than we had seen in Kepler. What's more is that TESS is, because of TESS's pointing, The continuous viewing zones point more out of the galaxy than Kepler did. Kepler pointed kind of along the galactic disk, and as a result, the stars that we had access to with Kepler were more younger stars that are located in the classical thin disk of the galaxy. But TESS's continuous viewing zones are pointed more out of the galactic disk, potentially giving us access to a fundamentally different population of stars. So with all of this promise that TESS delivers, we're now 4 years into the science mission of TESS. So where are the rotation periods? And the answer is complicated. TESS light curves are messy. Because of TESS's unique orbit, it orbits the Earth and the system once every 13.5 days, which is twice for every orbit of the moon around the Earth. Because of its unique orbit, it has weird systematics in every single light curve that are caused mostly by light scattered from the surface of the Earth, so Earth shine. But there are other effects as well that the telescope encounters as it orbits the Earth. This Earthshine signal is what you see in this light curve here. This is a raw TESS light curve, and you can see that there is this ramp that happens on a period of about 13.5 days. There is a gap in the middle of the light curve where the telescope is not collecting data because it has to do a barrel roll to transmit data down to the surface of the Earth. When it does that barrel roll, it messes with the thermal sensitivity of the detector, messing with its sensitivity to light. So all of these and more systematics confound rotation signals that are in TESS light curves. The effect is that any coherent signal on timescales longer than 13.5 days is essentially nerfed. So TESS rotation periods, at least long periods, are very hard. And it's not for lack of trying. There have been several attempts to get rotation periods out of TESS data, but all of them come up short. Canto-Martins et al. Used classic Fourier methods, frequency analysis to try and measure periods, and were not able to get any periods longer than 13 days. Ellis-Avalon, who all of us know, also used the classical conventional methods to obtain periods out of TESS data, but still was not able to get past 13.5 days. If you don't assume any kind of prior on the period you might expect to get, you can't get past TESS systematic barriers. Anything where you might expect a longer period just picks up on the 13-day signals that are in TESS light curves. Even Lucy Liu, who did assume some underlying prior on the period that she expected to get, she got past 13 days, but still experienced another kind of detection edge at about 27 days, and even less than 27 days, things were getting a little bit dicey. So the problem of rotation in TESS is hard. Let's pause for a second to think about where we are, the problem that we've been handed. TESS is delivering millions of light curves for stars that we want to probe for rotation, but the systematics in TESS have made rotation searches for long periods longer than 13.5 days very difficult. Conventional methods pick up on the systematics, and so what we need is a method that can, instead of removing the systematics, look at the signal, systematics and astrophysics underlying the signal, and tell them apart. If only we could look at these complex signals and learn the difference between the systematics and the astrophysical signal. Maybe the key word here is learning. Yeah. Now, you might know of machine learning in terms of classification. For example, every once in a while, you forget the difference between a muffin and a chihuahua. And you might need a neural network to remind you the difference. This is a silly illustration, but it does exactly what we needed to do. It shows that you can take two things that look stupidly similar, and with a neural network, the neural network can figure out what features are required to tell them apart. If a neural network can tell the difference between a muffin and a chihuahua, maybe it can tell the difference between systematics and rotation signal. So we're going to use a neural network to try and tackle this problem. There are some great examples of machine learning and neural networks in astronomy and astrophysics. These are some recent examples. Check out the papers because they're really, really beautiful examples of both regression and classification machine learning in astronomy. So that brings us to the overview of the dissertation. Our goal, if we choose to accept it, is to understand how the distribution of periods in cool main sequence stars is influenced by age, by angular momentum evolution, and by detection limits. And we're going to use TESS to get rotation in new populations of stars, using convolutional neural networks to see past TESS's systematic barriers. The objectives to meet our goal are to construct a deep learning framework to estimate periods, and then to use models to infer ages and convective timescales to understand how rotation behaves as a function of fundamental stellar parameters. The objectives influence our outline. There are three parts to this talk. First, we're going to construct a deep learning framework, build a neural network to do what we need to do. Second, we're going to use that neural network to estimate periods from real TESS light curves. And then third, we're going to use those periods and combine them with models and spectroscopic stellar parameters to see what we can learn about rotation in TESS as a function of fundamental stellar parameters. So starting with the deep learning framework. If you're going to use machine learning, especially supervised machine learning, you need a training set. So this is the first thing that we need to think about. For a training set, ideally we want a large set of light curves with known periods. You might think something like Kepler would be ideal for this, but Kepler is not quite what we need for this problem. There are a few reasons for this. One is that TESS's overlap with Kepler is pretty small. The overlap with the Kepler field gives us about 54 consecutive days of observation in Kepler. And if we're trying to get periods that are on the long end, 25 days and above, we need longer light curves to be able to get those. We're not going to get a good validation set with Kepler. Also, if we use Kepler as our training set, we're going to imprint whatever underlying distributions are in Kepler. We're going to imprint those onto our training set. And so that means if Kepler stars span a certain range of periods that aren't representative of other parts of the galaxy, we're going to imprint those biases on the predictions that we make with the neural network. We don't want to do that, that's bad. Also, Kepler can be wrong because there are real people using real methods to measure rotation periods. There is some amount of contamination of periods in Kepler. Susanna Gran in 2015 showed that as many as 30% of period predictions in Kepler might be wrong using the conventional techniques of frequency analysis. Also, Kepler gives us about 50,000 rotation periods. We need many, many, many more training examples in the order of 1 million if we want a neural network approach to be successful. So what about simulations? Simulations have their own limitations, but if we trust the underlying models, they can encapsulate a large number of underlying parameters. We can go beyond just rotation and look at things like spot evolution and whatever else we want to put in our models. We start with a model that's been tuned to produce spot evolution and light curves for the sun, and we add knobs to that model so that it can produce spot evolution and light curves for other stars, basically tweaking solar parameters to give us different activity levels, give us different spot lifetimes, give us different differential rotation patterns on the surface, and produce a set of model light curves. These model light curves are noiseless. They have no noise. They don't have TESS systematics. If we want our training set to look as realistic as possible, we need to include TESS systematics somehow. We can actually use real TESS light curves to encapsulate the systematics. So we actually take light curves from either galaxies, which we don't expect to be variable on timescales of a year, or even from stars that are in temperature ranges where they're expected to be quiescent from star spots. So we get these nice flat light curves that are flat, aside from the jumps and gaps that we see in the TESS systematics. We take those light curves and we combine them with the noiseless light curves from star spots to get our noisy, gappy, systematics, messy, rotational TESS-like light curves. We do this 1 million times and we can produce a really nice training set. The training set is called SMARTS TESS. SMARTS stands for the Stellar Magnetism, Activity, and Rotation with Time Series. The training set is downloadable from MAST as a high-level science product. SMARTS TESS contains 1 million TESS-like light curves. They resemble full-frame image light curves, so they're sampled at 30-minute cadence, and their duration is about a year to resemble stars in the continuous viewing zones of TESS. So we have this nice training set that we can now put into our neural network. The last questions that we need to ask are, what is our model and what is our data representation? So for the model, we go with a convolutional neural network, CNNs, not the news network, the neural network. CNNs are really nice at processing image data. And so that lets us take advantage of a 2D, two-dimensional input of the periodicity. which is a wavelet transform or a wavelet decomposition. So here I'm showing an example of a wavelet decomposition. It shows period on the y-axis. If I can get my cursor here, there it is. Period on the y-axis and time on the x-axis. So what this does is it shows a time varying periodogram. We can see how periodicity might vary as a function of time. This also gives us the added benefit of separating out some of the systematics from the rotation signal. The rotation signal shows up at a period of 16 days in this horizontal band of power, whereas some of the systematics, especially the jumpier systematics, show up as these vertical bands. They do contribute power in the horizontal band roughly every 13 and a half days, but we're hopeful that this data representation might help a neural network be able to disentangle the systematics from the signal. Also, neural networks have been around for a while. They're mature, they've been tested and used, and they take advantage of graphics cards on computers, so they are relatively fast to train. And so it's a nice model to take advantage of. So we have a neural network, we have a training set. The next thing that we want to do is train the neural network and then test its performance on a held out simulated test set. So the test set resembles the training set, but the neural network hasn't seen it, so it shouldn't be influenced by things that it's seen before. So then we ask the question, how does the neural network recover periods of simulated data? So here we've got the true period on the x-axis, the predicted period on the y-axis. We want things to show up on the one-to-one line, and they kind of do. There's some along there, but there's also this really weird horizontal band at 90 days. There's quite a bit of scatter around here. So let's unpack this for a minute and see if we can do better. The horizontal band, we know what's going on there. If there's any uncertainty in the rotation period prediction, predictions get biased toward the centroid of your distribution. So we have a uniform distribution of periods from 0 to 180 days. The middle of that is 90. So if the neural network looks at a light curve and says, I have no idea what this is, I'm just going to give it the median, it assigns it 90 days. Does that for a handful of stars, and boom, we get this horizontal band, a predicted period of 90 days. The scatter is also from underlying uncertainty in the light curves. We also have some recovery metrics up in the title of this. The recovery metrics are not great. We're not doing a great job at recovering things with high accuracy, but there is a part B to what we can predict with a neural network. In addition to the period, we can predict an uncertainty. By a special choice of loss function, we can predict the period as well as an uncertainty, and the uncertainty we can use as a metric for reliability of that prediction. If we take the uncertainty and we filter our predictions based on that uncertainty, we can throw out the worst predictions and keep the things that are more likely to be right. So when we filter by predicted uncertainty, this gets cleaned up a little bit. The horizontal band is gone. There's less scatter around the one-to-one line. And I should say this is the half of the test set. So we're looking at 50% of what we were looking at before, the half of the test set with the best fractional uncertainties. And so we still retain half of our data, but the recovery metrics are better. Things are falling along the one-to-one line. And most importantly, we're getting periods longer, successfully, longer than 13 and a half days, longer than 27 days, beating the test systematic barriers, at least in the simulations. How does this matter as a function of amplitude? As we're getting rotation periods, you might expect signals with higher amplitudes are easier to detect. We find that in the training set as well. In the black dots here, this is showing the unfiltered sample. Light curves with higher amplitudes are more easily recovered, or more successfully recovered. When we filter based on the predicted uncertainty, the disparity between the high and low amplitude signals becomes somewhat less. So basically what's happening is the filtering by predicted uncertainty removes the low amplitude signals more than it removes the high amplitude signals. This is what we expect. Things are behaving the way that we want them to if the uncertainty is telling us what we think it's telling us, meaning that is the prediction reliable or is it not? And then I've also got some dotted lines here to show you where Kepler stars live, just to give us an idea of what we might expect to see in a real population of stars. So that's great, but that's all simulations. What does this look like on a validation set of real stars? Unfortunately, there's not a whole lot of stars in the southern continuous viewing zone with prior measured periods. There's about 100 stars observed by the Kilodegree Extremely Little Telescope Survey, or TELT. It's extremely little. I love it. And so we can start with that. Of those 100 stars, about 25 of them have obvious rotation signal in their test light curves. So we're going to take those as the lowest hanging fruit and try and get the rotation periods. We take the light curves, we make wavelet transforms, we put them through the neural network, and we predict their periods. And here's what it looks like. So the Kelt period is along the x-axis. The neural network predicted period is along the y-axis. You can see that for the black points, which are the ones that make our fractional uncertainty cut, we recover them within uncertainties, even past 27 days. So we are recovering long periods of real stars using neural networks, and filtering by predicted uncertainty helps pull out those good periods. Things are behaving as we want them to. So that is part one, that we have constructed our deep learning framework. Now let's turn around and use it to estimate periods of stars and mass. We need to define a sample. If we're going to get periods for real stars, we need to define a sample. We start with the TESS input catalog, and we want to take stars that might reasonably be making spots. So they need to have a strong enough dynamo to produce spots so that we might detect them in rotation. And we're going to cast a wide net, so we're going to even go to higher temperatures than we probably need. We take everything in the TESS input catalog cooler than 10,000 Kelvin. And because we're targeting the southern ecliptic viewing zone, or southern continuous viewing zone, we take things with ecliptic latitude below -78 degrees. The next question is, which light curves do we use? There are a number of public pipelines to produce light curves for test stars. They come with problems. All of them have pros and cons, but all of them run the risk of, because they have really complicated systematics removal baked into their pipelines, they run the risk of removing rotation signals from light curves, basically throwing the baby out with the bathwater. We don't want to do that. So what we opt for is using the apertures provided by two well-established pipelines, the TESS SPOC, which is the Science Processing Operations Center pipeline, as well as the TESS Astroseismic pipeline. We take their apertures and perform custom photometry and use a lighter systematics correction than those pipelines use. The result is we're going to have some systematics left in our light curves, but hopefully we're preserving the rotation signals. That should be fine because we've already demonstrated that the neural network can see systematics and signal and pick them apart. That also means we're subject to the pipeline's target selections, and so we're downsampling our sample. This is just to show a little bit of the target selection. The TESS SPOC selection takes no more than 40,000 stars. We started with 600,000 from the TESS input catalog. The TESS SPOC selection only goes up to 40,000 in this order. They start with the 2-minute cadence targets, which are high potential science yield. They take, after that, they take planet host candidates, and then they take brighter than TESS magnitude 13.5 field stars until they reach 40,000 and then they stop. The TESS SPOC light curves or photometry pipeline processes all 13 sectors from the first year of TESS, and it gives us light curves or apertures for 38,000 stars with temperatures cooler than 10,000 Kelvin. TASOC, on the other hand, gets all TIC objects brighter than TESS magnitude 15. They use larger apertures, which means their light curves are less noisy. The downside is they've only processed sectors 1 through 6, so we only have apertures for half the length of light curves that we get from TESS SPOC. But there's still a lot of light curves, a lot of apertures available from this pipeline because they've gone down to TESS magnitude 15. We make a cut at 5,000 Kelvin this time because we're only trying to get the things we're most likely to see in rotation. And so we get 30,000 stars, less than 5,000 Kelvin. This is what our sample selection looked like before. Now that we've applied the pipeline restrictions, this is what it looks like now. We've lost some of the hot stars, but that's fine. We really care about the things on the cool end, which are more likely to have rotation signals. So we have our stars. We've done photometry using pipeline apertures. We can put them through a trained neural network and get rotation periods. So let's take a look at what the period distribution looks like. To prime you, I'm going to show Kepler one more time. So this is Kepler again. with the features that we saw before, things like the short period edge, the long period edge, the pileup from weakened magnetic braking, as well as the gap here in the cool stars. When we overplot the new TESS periods, this is what we get. So now we can compare and contrast. There are similarities and differences. We do a good job at recovering the short period edge. It's in the same location with the same slope as what we saw in Kepler. We also have the gap in the same location, roughly the same slope. It even disappears at roughly the same place it disappears in the hot stars in Kepler. That's promising. We have some slowly rotating M dwarfs. These things have periods of between 50 and 75 and even higher days, which is really long for TESS, longer than we really expected to get. There's some things over here. These are probably not real detections. There might be subgiants in here, but these things are expected to have really low amplitudes, and when you measure their amplitudes, they are actually pretty small. Probably some spurious detections, so there's a little bit of contamination that needs to be dealt with. We also have a little bit of a detection edge. This edge is at 27 days, which is the sector length of TESS light curves. We still have to stitch our simulated light curves together. And so there is still some nerfing of systematics at 27, or nerfing of signals at 27 days. And so even though we include this in the training set, there is some behavior at 27 days that the training set is either not adequately capturing, or it's that the periods are so much less certain past 27 days that when we make our uncertainty cut, we're throwing them out. And so we see this edge at 27 days. This is the first takeaway, which is that deep learning lets us probe long enough periods to recover the features seen in the Kepler period distribution. These were previously off limits to TESS, but deep learning has let us get to these features with TESS. How does this look as a function of amplitude? This actually behaves as we expect. As you raise the floor on the amplitudes that we're allowed to see, we lose stars where we expect their signals to be at low amplitudes. Things that are hot, things that are spinning slowly, should not have a whole lot of spot modulation, and so they should be the first to go. Things that are up in, if I can get my cursor back, things that are up in this corner. This is where the smallest amplitude signals should be, and so it's promising that they're the first to go away. You raise the floor even more, it chops off another chunk of this. This actually carves out lines of constant Rossby number. Rossby number is the ratio between the rotation period and the convective overturn time scale. Rossby number scales with stellar activity. So that means as we are raising the threshold on the activities that we're allowed to look at, we're chopping off things with at certain levels of Rossby number. So this is doing exactly what we expect it to do. That's promising. Another view of this as a function of amplitude is we can show the distribution that we showed before, but now paint it a color based on its variability. And this is what I'm showing here. The same variability is now the color scale in this plot. So the things that are hot and slowly rotating have very low variability amplitudes at a fixed temperature. Things that are rotating rapidly have high amplitudes because they should be more active. Things that rotate rapidly are more active. They have stronger magnetic fields. They produce more spots and should have higher variability amplitudes. You increase in period or you spin down, you get less activity. And so you should see fewer or smaller rotation signals. And that's what we see in fixed temperature bins. There's another interesting feature happening at about the position of the period gap. In this little blob, there is a dip in the variability amplitude. This is something that was seen by Timo Reinhold in, I think, Kepler and K2. And he used that to suggest that the gap was produced by this competition between bright faculae and dark spots, where they cancel each other out, their amplitudes become small, and so we detect fewer stars in this regime. Is that what's going on here? It could be. It's interesting that we see this feature in TESS as well as Kepler and K2. This brings us to our second takeaway. We can reproduce key features of this distribution in TESS. We get the gap, we get the lower edge, we get slowly rotating M dwarfs, and we get changes in variability across the period distribution. And that takes us into the third and final part of the talk. Now we're going to use the rotation periods that we've obtained fit models to them using spectroscopic stellar parameters and look at things like detectability across these fundamental parameters. So thanks to the abundance of data from ground-based spectroscopic surveys like Apogee, we have precise and homogeneously determined temperatures and compositions for many of the stars in our sample. Of the stars that have reliable periods, 3,400 of them have apogee spectroscopic temperatures and abundances. I'm showing a histogram here with temperature on the x-axis, metallicity on the y-axis, just to show you where the stars with apogee parameters live. We have a lot between 5,500 and 6,000 Kelvin. There's fewer going into the cool stars. But I'm going to paint this now with the detection fraction of rotation in each bin. And so we're going to see where stars are more preferentially detected in rotation and where they're less detected in rotation. As we might expect, cool stars, which have deeper convective envelopes, are more preferentially detected in rotation. Things with deeper envelopes should have stronger dynamos, produce more spots, and be easier to detect. There is a little bit of a cutoff at around 5,200 Kelvin, where the detectability starts to decrease with increasing temperature. And in this little range between 5,200 and about 5,700 Kelvin, there's maybe a vertical trend with metallicity. With increasing metallicity, we see increasing recovery of rotation. There are two things that could cause this. One is that increasing the metallicity of a star increases the opacity in its envelope, which deepens the convective envelope. As you deepen the convective envelope, just like we said before, you get a stronger dynamo, more spots, and more amplitude more amplitude in the photometric signal. So it could be metallicity inflating the envelope. It could also be an age effect. Because of galactic chemical evolution, things that are metal rich, so things in the upper part of this small range, things that are metal rich tend to be younger. Younger stars rotate more rapidly and also have stronger dynamos, and so we might expect to detect them more readily in rotation. So it could be an age effect from galactic chemical evolution. It could be metallicity puffing up the convective envelope and making things easier to detect. We need to do more tests to suss out exactly what's happening here. But as we expect, rotation is more easily detected in stars with deeper convective envelopes and in younger stars that spin faster. With the abundance of spectroscopic parameters, we can now fit models to these stars with rotation periods and precisely characterize their ages, their masses, their convective overturn timescales, anything that you can fit into a stellar evolution model. We can now fit models to these stars and infer. I do this using Kiyohoku, which Jen mentioned in the introduction. It's my pride and joy. It's my 699.2 project. It is a interpolator, and I use it to interpolate models of stellar evolution, particularly ones that include evolution of rotation with time, so that we can use things like gyrochronology to estimate ages using rotation. If you want more information, I have a poster on the wall over there. You can learn all about it. So here is basically the plot that's on the poster, where we do gyrochronology using a sample from Kepler. We have periods and we have apogee temperatures, metallicities, and alpha element abundances, and we can fit models to these stars in Kepler to infer ages. We then use those ages to look at galactic chemical evolution trends in Kepler. There's a lot going on here, so I'm just going to highlight things that I want you to see. There are two main populations of stars in this diagram. There's one that is alpha poor and young. This is the classical thin disk. And there's another sample that is older, a little bit more alpha rich, kind of a little bit of a spread. This is the classical thick galactic disk. The hex bins in the background of this are from another work doing chemical abundance trends in Kepler seismic stars. And so they're just shown there to show that things are falling about along the same trends as a function of age. Now that we've done this in Kepler, we can turn and use the same machinery to do this with TESS. And here is the first look at gyrochronology with TESS stars. So we see basically the same trends, a little bit of differences. We have the classical thin disk, which is alpha poor and young. We have maybe some stars in the classical thick disk. They go up to pretty high alpha. They go up to pretty high ages. There's many fewer here because old stars are spinning slowly. They have smaller photometric amplitudes. They're much harder to detect in rotation. And so we just get fewer stars there because of detection limits. There's also some young, apparently young alpha-rich things. These blue and purple bins that are up here. These are likely to be the products of stellar mergers. So they're things that are truly old, truly alpha enhanced, but they merge and it screws up their periods, which screws up the ages that we infer. Fourth takeaway, which we get from gyrochronology, deep learning now empowers the rotational characterization of stars in TESS. The last thing we're going to look at is the importance of spottedness. As we might expect stars that have more spots to be more easily to detect in rotation, more easy to detect in rotation, and we can actually use things like spot filling fractions to look at the importance of spottedness in our detection of rotation. Through the magic of collaboration, we have spot filling fractions measured by Lyra Tsao at Ohio State using apogee spectra. Her method is basically to take the spectra from apogee and fit them with two different temperature component models. The spots that are on the surfaces of stars are cooler than the ambient surface, and so we should see in the spectra two different temperatures. So she fits these two component models and pulls out a spot filling fraction as well as a contrast of the dark spot to the ambient stellar surface. This method is particularly sensitive to binaries, and so we want to be extra sure that we clean our sample from any binaries. I do this removing things with the Gaia renormalized unit weight error, or RUI, greater than 1.2. This is similar to what Travis Berger does in his catalog. I also remove things that have a Gaia magnitude at excess. Basically things that previously fell along the upper sequence of binaries on this diagram. There's my cursor. Things that were up here before I've cut off because they are likely to be binaries. So now we have this extra clean sample of 958 stars. They should be removed, have binaries removed from them, and we can see what the spottedness is in the sample of stars. Down at the very coolest end in the M dwarfs, things are pretty spotty. This is to be expected because M dwarfs have very deep convective envelopes, strong magnetic fields. They should be producing lots of spots. But there's also this interesting little bump in the K stars where the spot filling fractions are high. I want to take a quick zoom in on this region to see if we can if there's any difference in the detection of rotation as a function of spot filling fraction. The way I do this is I split this little sample into two groups, the group where we have periods detected and the group where we did not detect periods. I look at their distributions of spot filling fraction and see if there's any significant difference between those two distributions. And here's what the distributions look like. I have just the plain old histogram on the left. The period detections are in the blue bins. The non-detections are in the orange bins. There's about 100 stars in each of these two samples. The distributions are pretty similar. When you look at the cumulative frequency distribution, I can maybe squint and start to see that maybe things that are more spotty are more likely to be detected in rotation. But a KS test is the thing, which is a Kolmogorov-Smirnov test, is the thing that we use to tell whether two distributions are drawn from the same underlying distribution, two samples drawn from the same underlying distribution. And a KS test says that no, there's not really any significant difference between these two samples. So as much as I want to squint and make conclusions about this, I'm going to rely on the statistics to tell me that no, there doesn't seem to be anything going on with spot filling fraction, which is in itself interesting because our expectation was that spot filling fraction might have something to do with the detectability of rotation. That's all I'm going to say about that for right now. We can also take spot filling fraction and look at it as a function of rotation. Now that we have periods for these stars, we can overplot the period distribution colored by spot filling fraction and see what it looks like in the context of other stars. So we're starting again with the open clusters. The And just as a reminder, the behavior that we see in the open clusters is this stalled breaking, especially in the green points, NGC 6811, as well as Rupert 147 at 2.7 gigayears. These interesting stalling of the breaking and then restarting at some point later. So when we plot the test stars colored by spot filling fraction, this is what it looks like. Now this is interesting. Don't take my word for it. I'm going to try and convince you why it's interesting. In the same region of temperatures that the stalled breaking is happening, the breaking is stalling and restarting, stars appear to have elevated spot filling fractions. Now, we didn't necessarily expect stars to have elevated filling fractions in this region, aside from just being at the cool end with deep convective envelopes that have strong magnetic fields and many spots. So the fact that this elevation in spot filling fraction happens at the same place as the stalled breaking in the clusters means that maybe they have some common cause. This also happens to be where the period gap is in the test distribution, as well as the dip in amplitude. And so there are 4 different features that are happening all in the same regime of temperatures. Could it be the same thing powering these? Maybe. I'm going to be real speculative and real cautious here. But the spottedness increasing in the same place where the breaking stalls, in the same place where the gap occurs, suggests that there may be a common cause. So as we look ahead, TESS has been active for 4 years. It still has a lot of work left to do. Even in the last 4 years, TESS has observed more sectors. It's observed the south again for another year. It's also observed the northern ecliptic hemisphere, which means we have a whole nother continuous viewing zone to look at. And as it has observed those, we can even look beyond the continuous viewing zones at more sections of sky to try and get periods across the entire sky. So we have more sectors to look at with TESS. We have more sky to look at with TESS. And according to George Ricker, just last week at the task meeting in Leuven, TESS might still be active in 10 years. So we have a lot to expect from TESS, and we're very hopeful. Besides that, we can start looking at more than just rotation. The models that I showed you earlier, the butterfly models, have, in addition to rotation, they have spot evolution, they have surface differential rotation, they have magnetic cycles. We can start to bake those into our neural networks and try and pull them out of light curves to see what we can get with TESS. So to summarize, I have the main takeaways that I've showed you throughout the talk here. The takeaway is that deep learning gets us past TESS's systematic barriers. We can now get long rotation periods with TESS where they were previously off limits. We can reproduce the features seen in Kepler's rotation period distribution. We can use those periods to characterize stars and start to look at what causes these weird features seen in the period distribution. There's a lot more to be learned from TESS, and there is no end in sight. The future, to use a cliche, is very bright. Thank you. I want to end with acknowledgements because doing a PhD takes a community effort. And everyone in this room has been instrumental to getting us to this point. So to start with Jen, my advisor, to be your first student is what an incredible time it's been. As you have seen me grow into a functional human being in science, I have seen you grow into a very proficient advisor. From the beginning, you have been able to pinpoint my weaknesses and then help me fill them in using just the right acutely applied pressure. So thank you. It has been so much fun, and I look forward to just being like collaborators. That's kind of neat. I'm gonna put this here. Mike Liu's not in the room. Sorry, Mike. Also want to thank my committee, Dan, Ben, Shudong, Peter, and Monique, especially Monique and Shudong, because you guys are in Europe. It's late for you. Thanks. I hope you guys are doing well. You guys are the perfect handpicked committee for this project. There are elements of the sun, of time series, of machine learning, of stars, and of rotation, and there's lots of math and numerical modeling. And so you guys are the perfect combination to advise me on this. And I've appreciated our conversations and all of your insights into making this work what it is. Collaborators who have worked on this with me, Joe Lama, Brandon Kwok, Lyra Sao, Mark Pinsino, Jamie Tyar, Savita Mathur, as well as the Ohana here at IFA. I have some names listed here: Laura, Amy, Faye, Wayne, Raja, Gavin, George, Kurt, Evelyn, Melissa, Caroline, Bill. There are so many people that make this place a home. I am grateful for all of you because PhDs would not be possible without the support of our staff. So thank you. Faculty, special shout outs. I want to shout out Dave Folin and Josh Barnes. You guys were my first research advisors here, and you helped me ascend the steep learning curve of grad school. So thank you for that. I have to acknowledge the outreach titans, Roy, Carolyn, and JD. Outreach has been one of the most important parts of my grad school career, and they are such hardworking people who help us to reach out, but also learn from this awesome community that we get to spend 6 years in. For the grads, oh no. Oh no. I've always said that the best thing about the IFA is the grad community. There is so much support. There is so much family in this community. And I'm so grateful for you guys, especially my cohort, Deep, Erica, Ashley, and Ryan. It's very convenient because your last names spell out ABCD. But I am so grateful for you guys because you have been my family and been my anchors of support through all of the highs and lows. So thank you guys. Grateful to our Kaimuki Christian Church Ohana. I know some of you guys are watching on the YouTube stream. Thank you for looking out for us these past 6 years. We could not be here without you guys. Also have to thank my friends at Morning Glass. I love coffee. I love Morning Glass. This PhD is as much theirs as it is and finally, my family, my mom, Cheryl, my dad, Randy, my sister, Elise. You guys were my first teachers from the beginning. When I said I wanted to be an astronaut, you didn't ridicule me. You pursued me to keep learning, to keep growing, and you told me to never stop. And so here we are. Thanks, guys. And my wife, Natalie, who's here, you have been just a rock of support. You have given me your support and love and patience and kindness when I didn't deserve it. And I'm so grateful to you. And finally, I'm grateful to everybody here for your support, for being here, taking the time out of your day. Let's do some questions.
Questions for Zach? Yeah.
The previous 27-day detection limit for rotation periods, does that come from just the sector length, or is it like a harmonic of the orbital period or something?
It is probably both of those things. The main thing is the sector length, because the sector length is 27 days. To make a year-long light curve, you have to stitch these 27-day things together. There's not a good way to do like an absolute flux calibration from sector to sector because TESS targets fall on different pixels between every sector. Because as the telescope rotates, things fall on different pixels. So there's not a great way to stitch these together yet. There are people actively thinking about the best way to stitch them together and try and preserve those intersector trends. I am not them. They are titans. So yeah, it's mainly the stitching of 27-day sector length.
Okay, let's do Suji.
I was wondering about the loss function that you used for the uncertainty filtering. What you spoke, you just said loss function, but can you elaborate more on how you chose that?
Yes, I think I have a slide for this. Yeah. So I use a log Laplacian loss function. This is kind of the equivalent of using a, so like the kind of more like simple loss functions are things like mean squared error or mean absolute error. The analog to mean squared error is log Gaussian. And so that lets you do mean squared error with uncertainty. A log Laplacian is the analog to median absolute error, which lets you do uncertainty with that. And so this is the form of it. It relies on the difference in period not squared, as you would see in a Gaussian. That the choice of this loss function, I'd initially started with the log Gaussian, which still gives you the uncertainties, but because it depends on the error squared, we were having more issues at the edges of the period distribution where the range of predicted period was getting squished. Because if the error is squared, it basically pulls things stronger away from the edges. We didn't want to do that. We wanted to try and fill that range as much as possible. So we used the log Laplacian to try and keep the predictions filling the range.
You.
Do you mind going back to, excellent job, by the way. Do you mind going back to the first look at TESS long period light curves when you overplotted it with Kepler? Like black and red.
Yeah. Sorry, I'm doing the thing Ben hates and skipping through all of my slides. Yeah.
There we go. Do you happen to know if that 20, I understand why the 27-day kind of shelf is there, but do you know why it's more prominent like at the hotter edge, or appears more prominent at the hotter edge?
I think what's going on here is that there are just more stars in that range of temperatures, and so it's basically like piling things onto that edge. It's just kind of many fewer stars in the hot, or in the cool end, and so it's just not as many things there to build up a pronouncement of that edge.
Okay, so it's just a visual thing. You think if you had more stars in that bin, that it would be there as well?
I think so, but I don't know so.
All right.
The choice of the convolutional neural network strikes me as counterintuitive. Normally, I think about images, as you said. When you're feeding it those rolling periodograms as images, it seems like there are a bunch of different knobs that you might want to tweak, like kernel size and whether it's in frequency space or not. Could you talk a little bit more about how you settled on CNNs and what you played with when feeding it information like that?
Yeah, great question. So from the outset, we had the idea of using CNNs. We didn't try a lot of other architectures. There was at one point where I used just a simple like feed-forward neural network using just the light curve to try and pull things out. It had some amount of success on like pure sinusoids. It was very, very early, just like testing stuff out. But the choice of CNN was really motivated by using the wavelet decomposition as the input, because one of the things that I eventually want to look at is surface differential rotation. We might expect that to show up in the wavelet transform as a change of periodicity with time. And so using that 2D time varying periodogram means that we can use something that's made to process images. And so that was the CNN was the natural choice for that. For playing with all of the hyperparameters and such. So I experimented with different kernel sizes, didn't find a whole lot of difference using different choices. Played with the number of layers as you do when you're trying to build an architecture. I have some stuff about optimization here where I have just used a handful of different architectures. I didn't do anything like fancy and automated for this, but that's something for maybe future me. So here I'm showing just like recovery for different runs using these different architectures, the recovery of prediction versus true, as well as the learning curves, how the loss is as a function of time. Not a whole lot of difference between successive choices, but I still use the thing that gave me the optimum output.
I know that I think it was your takeaway 5 that said that the rotation gap coincided with the spottedness, which also coincided with the magnetic braking. I know you were very cautious with suggesting this, but what do you think that this common cause would be physically?
So some of the causes that we've talked about for the gap, right? So one of the ideas about like the fundamental change in the nature of braking is this thing that is called core envelope decoupling. So we assume that stars in the like classic schematic like spin down, we assume that stars rotate as a single rigid body. But if you allow the envelope and the core to decouple and undergo different rotational evolution, you can kind of start to produce that gap. Jason Curtis in his 2020 paper kind of demonstrated using some core envelope decoupling models that you might be able to produce the gap. Trying to think about how that might result in a changing F spot or like the spot filling fraction. There are ways that that gets uncomfy because you have to start thinking about changing the actual dynamo that's producing the spots. There are the idea of like competing spots and faculae, that makes the variability dip. There is some stalling and braking, and so maybe those kinds of things are related. I had an idea yesterday of maybe like something happening with the stellar wind. If you increase the spottedness, you get a more complex magnetic field with more closed lines, and so not as many winds get out. That might cease the braking. You can't brake without wind, and maybe that has something to do with the number of spots. There's a number of things, a lot of people thinking about this problem. If there is like some smoking gun that will fix all of these, we haven't found it yet. Those are some of the ideas.
I want to check if there's anybody on Zoom. I cannot see if you posted a question, so if you could unmute and maybe pop your camera on if you have it, that would be helpful. Doug, I see your microphone showing. I don't know if you have a question.
Not a question, but a big congratulations to Zach and Ashley. I'm over in Montreal right now, and I snuck away from the meeting to catch Zach's presentation. Ashley, yours is queued up. I got double booked yesterday. I'm going to watch it right after the one. Congratulations to both. These are really not just impressive, but inspirational for me to see this sort of culmination of so much work in our graduate students. And I can't tell you how proud I am. This is part of the highlight of my job, the work of you and your collaborators and the whole HANA. So great job to both of you. I will be on an airplane first thing tomorrow morning and back in Hilo Friday. And looking forward to the future Gainesville and Seminole games, Zach. The conversation we've had earlier. I'll be thinking about you while Florida State beats up on the games.
We'll see who beats up on who. I'll be thinking about you too, Doug.
Great job.
Thank you.
So, all right. Rob, did you have a lingering question before we go into closed session?
I have a question.
Yeah, go for it.
So it's actually two questions about the systematics. So they look pretty bad, and I just wondered, were they anticipated when they launched the spacecraft? And so that's the first question: were they anticipated and modeled correctly when they built it? And then the second question is, when you showed your figure where you were adding the systematics into your synthetic light curves, you showed only the noise after a lot of systematics had already been removed. So were you adding it at this point after like some of the pre-processing goes on that removes most of the systematics and you're dealing with residual systematics, or were you adding it into the full systematic problem?
So I'll do the second question first. I am taking things that are basically residual systematics and combining those with light curves, but they still undergo the same stitching procedure that the regular light curves have to go through. And so that's one of the big things that are facing it. But the Earthshine signal, the 13.5 day band ramp, has mostly been subtracted out. And so we're just dealing with a little bit of residuals in both cases. Whether they anticipated the level of systematics, every time, this is a nice way to say this.
They shifted the camera up.
Yeah, I mean, I don't think the level of systematics that we're encountering were anticipated. They anticipated some. I think things have been a little bit worse than they anticipated. And George Rickard has some thoughts on trying to mitigate these systematics. He says there are people working on them. He's very optimistic. I think I'm going to have a job for a while.
Right. Any fine, because we should probably get down to grilling. Anybody else lingering? Yeah, one more in the back. And then
How do you ensure that the simulations of the light curves didn't bias your equals instead of using it.
Yeah, that's a great question because, I mean, choosing a simulation set, you have to make sure that you understand the underlying distributions so that you don't accidentally bias your predictions in ways that you don't want. We did this in just kind of the underlying distributions of the parameters of the simulation. So like rotation period, we left in a uniform distribution because we didn't want to bias things towards short or long periods. We did a similar thing with like the activity level. Things are uniform in log space. And so we didn't want to have like more things that are at low activity levels than at high activity levels where the sun is like right in the middle. And so we were very careful about the choices that we made of those underlying distributions. So far, we've only looked at period, trying to predict period using neural networks. And so this is the one that I'm most comfortable with because it's just a plain old uniform distribution. And so it's like an uninformative prior, essentially. But we're going to be thinking about these other distributions as we might try and think about pulling those parameters out of light curves as well.
Okay, thank you, everybody. Let's give Zach.